Okay, so last time we started applying the principles of quantum mechanics. We started with the free particle. So today we're going to extend that a little bit. We're going to impose boundary conditions on our free particle. So it's no longer a free particle. We're going to say it's going to be confined between this location and that location. So we call it a particle in a box. Okay? So consider a particle that's confined to a one-dimensional box such that the potential energy is zero inside the box. So that means there's no, if it's zero, it's really irrelevant whether it's zero or not, but what's important is that it's constant inside that box. So if the potential energy is not changing, then we can just conveniently just take that value as zero. So it's zero inside the box, and then outside the box we're going to assume it's infinite. What does it mean if potential energy is infinite? That simply means that we are insisting that we cannot find that particle outside the box. We're going to constrain it, we're going to confine it to that box. So we have, oops, oh, what did I do? All right, so if you have your box right here when x equals 0, between x equals 0 and x equals L, all right, so your particle is going to be within that. So potential energy is 0 there. Once you get to x equals 0, this is your x-axis, your potential energy goes to infinity. So beyond this one, potential energy is infinity, and beyond x equals L, your potential energy is also going to be infinity. Okay? So what would be the time-independent Schrodinger equation for this problem? Well, for inside the box, what's the Schrodinger equation? Sydney, time-independent Schrodinger equation. Most fundamental equation. H hat Hamiltonian applied on psi equals energy times psi. That's always our starting point when dealing with any system. We solve the time-independent Schrodinger equation. So what's our Hamiltonian operator for inside the box? Hamiltonian is the operator for energy, so it's equal to the kinetic energy operator, which we're going to call T hat, plus the potential energy operator V hat, applied on psi. That gives you E, the energy, times psi. Let's see if you remember what's the kinetic energy operator for a particle in one dimension. Don't remember? Negative h bar squared over, you remember now? Still no? Over 2m. Me? What's the next one? Okay, second derivative with respect to x. Okay. And what's our potential energy operator? What's the potential energy inside the box? Is 0. So potential energy operator is just a multiplicative operator. In this case, we multiply by 0, whatever it operates on. So that's your Hamiltonian operating on psi, gives you back E psi. All right. So we've seen this problem before. This is essentially the same differential equation we saw when we did the free particle problem, right? Same thing, except that in this case we will have to apply the boundary condition, that the constraint that psi must be 0 at the walls of your box, okay? Because we don't want to find the particle outside the box. Whereas in the free particle, we had no restrictions on where the particle could be. So outside the box, then we're saying that psi must be equal to 0. If the probability of finding the particle outside the box is 0, then it must be psi squared must be 0 everywhere outside the box. So outside the box means x less than 0 and x greater than L. Inside the box, we've seen this problem before. We already know the general solution to this differential equation. Psi equals C1 e to the ikx plus C2 e to the negative ikx, where C1 and C2 are constants, right? You have a second order differential equation. So your general solution would be a linear combination of two linearly independent specific solutions, e to the ikx and e to the negative ikx. All right. So remember what k was for this? It's k would be equal to square root of 2 times the mass times the energy over h bar. Okay. So you have to go back to the lesson on the free particle problem. It's essentially the same problem, and the same. We're dealing with the same k here, so it's square root of 2 me over h bar. Now, like I said, so far what we have at this point is a free particles problem until we impose the boundary condition. So the boundary condition we're going to impose is that psi must go to 0 when x equals 0. Why? Because psi has to be continuous. So outside the box, beyond x equals 0, below x equals 0, it's 0. So your function must be 0 at that point, at x equals 0, when approached from either side. Okay, so it must approach 0. And at the other end of the box, psi at x equals L, psi must also be equal to 0. So let's see what happens if you apply those boundary conditions. Well, you'd be able to show that in order to satisfy the condition that psi must be equal to 0 when x equals 0, then you'd be able to reduce that expression to psi equals a sine kx. Let's see how that's done. Okay? So let me scroll down here. What did we say the general expression for psi was? Psi is equal to C1 e to the ikx plus C2 e to the negative I kx. So if we insist that if x is 0, psi is 0, this is a boundary condition, then we can plug in 0 for psi equals C1 e to the ik0, right, plus C2 e to the negative ik times 0. So what is e to the 0? That's 1. This is 1. And this is e to the 0. That's also 1. So we say 0 must be equal to C1 plus C2. So we can simplify our psi now. We can say that C1 must be equal to negative C2, or C2 equals to negative C1, right? C1 equals negative C2, or you can say C2 equals negative C1, either way. So let's simplify our psi. What do we have now? Psi is going to be C1 e to the I kx plus, instead of C1 we write instead of C2 we write negative C1 e to the negative I kx. Well, we can factor out C1. That's e to the I kx plus e to the negative I kx. Do you recognize that? Oh, that's right. That's negative. So do you recognize that? We've seen that lots of times already. E to the ikx minus e to the negative ikx. Euler formula. So that's going to be equal to C1. All right, so let's go ahead and expand it. Cosine kx plus I sine kx minus 1 cosine kx minus I sine kx. So your cosine kx cancels out. That gives you what? C1 times 2I sine kx. So C1 is just an arbitrary constant at this time. So 2i is also a constant. A constant times a constant is just another constant. So we're just going to lump all of these constants together. We're just going to call that A sine kx. Okay, so psi, in other words, of all the possible solutions to that original differential equation we have, by imposing one boundary condition, we've eliminated some of those solutions. We are now restricted to just those solutions that are of this form. Okay, so A psi would be equal to A times sine kx. So let's go back to, so that's your first boundary condition. Now, your second boundary condition, psi must be equal to 0 when x equals L. Okay, and it's going to lead to this conclusion right here that k times L must be an integer multiple of pi. So it's going to be n pi, where n can be 0, 1, 2, 3, and so on. All right, let's look at that. Let's go back here. We have a new boundary condition to apply. What's our boundary condition now? Psi equals 0 when x equals L, right? So 0 is equal to C1 e to the I k L plus C2 e, oops, oh, we don't need that anymore, I'm sorry. We've reduced it now, right? So we've already simplified it. It's A sine kx, right? So we now say psi is equal to 0 when x is equal to L. So we say psi equal 0 equals A times sine k times L. All right. So that's our restriction now. So we've narrowed down, we're going to be narrowing down our solution, possible solutions, to those that would satisfy this condition. Okay, so what would make A times sine KL equal to 0? A is obviously not 0, right? We can't make A 0 because otherwise we have what's called a trivial solution. Psi will just be 0 everywhere. And if psi is 0 everywhere, that means the particle does not exist. So that's really not an acceptable solution. So A has to be some finite number. So we want sine KL to be 0. How do we make sine KL equal to 0? What are the possible values of KL that would make sine KL equal to 0? So sine 0, so if you review your unit circle, sine, it would be equal to 0 at theta equals 0 and theta equals pi, right? But it can be 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, or you can go negative pi, negative 2 pi, and so on. So you're saying then that KL must be an integer multiple of pi. So that's a restriction. So that tells you that there is a restriction on K, right? K, in other words, will just be, we rearrange this, solve for K. K is just going to be n pi divided by L. So K must be an integer multiple of L, of pi over L. So what happens to our solution now? So instead of psi equal to A sine kx, we can now write it as what? A times sine. Instead of k, we now say that there are restrictions on the values of k. K must be equal to n pi over L. So n pi x over L. So this is the solution to your particle in a box problem. What are the restrictions on n? N must be equal to an integer, right? So let's go back to the top of that slide. Here is your solution so far. Okay? We're going to examine these solutions now to see if any of these possible solutions are acceptable or not, because we have to make sure that whatever solution we get has to be consistent with the physical constraints we have on our system. All right? So let's look at the next slide. Let's consider our solution now. At this point, we have psi equals A times sine n pi x over L, where n must be an integer. All right, let's apply the normalization condition. Okay, we want psi to be normalized. That means what? It should be, remember our interpretation of psi squared, psi star psi, is that it's a probability density function. So if you integrate it over all possible locations of the particle, in this case we have to integrate it, so integration d tau means over all possible locations. So if we integrate it from x equals 0 to x equals L, the integral you get must be equal to 1. So integral of psi squared dx from 0 to L must be equal to 1. Okay? By making this, applying this normalization condition, we will be able to figure out what A is. Okay? So A, you can think of A then as your normalization constant, because sine n pi x over L by itself is not normalized, as you can see if you were to do the integration. Okay, so at this point, a useful integral that you could use to solve for A, right, is this one right here. Integral of sine squared ax dx would be equal to a over x over 2 minus 1 over 4a times sine 2ax plus integration constant. If you apply that, you should be able to show that a is equal to 2 over square root of 2 over L. Okay, so we can update our solution now. It should say psi is equal to square root of 2 over L sine n pi x over L. Actually, what we find here is that that's the absolute value of A. It's actually square root of 2 over L. Okay, so A could actually be anything whose absolute value is square root of 2 over L. Okay, so it can be a complex number if you want. You can make it a negative number. All right. Okay, so how do we do that? Let's work that out. Let's just go through the math. Okay, we want, remember, we want A sine n pi x over L. Okay, take the complex conjugate of that, you get the same thing, right? Except you're going to have A star. So let's just take the absolute value squared dx from 0 to L is equal to 1. How do I solve for A? I factor it out with my integral, right? So absolute value of A squared, integral of sine n pi x over L, the whole thing squared. I don't need absolute value there anymore because the sine of a real number is also a real number. Dx from 0 to L is equal to 1. It's your typical normalization problem. And so absolute value of A squared is 1 over the integral of sine n pi x over L squared dx from 0 to L. And like I said, if you apply that identity right there for integral of sine squared dx and plug in the numbers, let's make that your homework. Okay. Then you're going to get, this is going to be, you'll find that this is going to be equal to 2 over L. All right, so what do we have so far? We have inside the box psi equals square root of 2 over L times n pi x over L, where n is equal to, okay, I said something about n cannot be 0. Okay. There's one other thing you need to be aware of is that n cannot be equal to 0 if we want our function to be normalized. Why? What would happen if n is equal to 0? What's sine of 0? So if n is 0, psi would just be 0 everywhere, right? Psi would be equal to 0 inside the box. Psi is 0 outside the box. What's the integral of 0? What's the area under the curve? If you plot 0 versus x, there's no area. It's 0. Probability of finding the particle inside the box would be, so n equals 0 is not allowed. Okay? So you can see here, and this is a common thing you'll find when you apply quantum mechanics to specific systems. Every time you impose a boundary condition, you impose physical constraints on your system, that's when you see quantization. Okay, so the phenomenon of quantization just comes out naturally from the mathematics. When you apply your boundary conditions, that's when you see quantization. So psi cannot be equal to 0 everywhere, so we cannot allow n to be equal to 0. All right. So now, here's our wave function so far. Here's our solution so far. Psi equals square root of 2 over L sine n pi x over L, where this n is restricted now to non-zero integers. Okay, so we've narrowed it down further. And like I said, this square root of 2 over L doesn't really have to be positive. It can be negative. It can be complex. So anything that has an absolute value of square root of 2 over L would be an acceptable value for that normalization constant. As a matter of convenience, we just take the positive value. All right. Now, if you want to specify a complete set of eigenfunctions, you only need to specify linearly independent functions. There's no point in including functions that are linearly dependent in your set. So if you remember, sine x and sine negative x are not linearly independent. Why? Sine of negative x is just equal to negative of sine x, right? So the sine of negative x is just negative 1 times the sine of x. So those two functions, sine of negative x and sine of x, are not linearly independent. So, well, that's what you get if you put something like n equals 1 and n equals negative 1. So a function with n equals 1 and a function with n equals negative 1 will not be linearly independent. So you can then say then that if you have n equals 1, 2, 3, 4, and so on, that by itself is already a complete set. Or you can take n equals negative 1, negative 2, negative 3, and so on. That would be a complete set. As a matter of convenience, we just choose positive values. There's nothing wrong with using negative values. So if you had a true or false question that says, n for a particle in a box, n cannot be a negative number, that's false. It can be a negative number. It's just that, you know, as a matter of convenience, we just like to make it simple, so we just choose positive numbers. Okay? So here's our final set of solutions for our particle in a box. Psi would be square root of 2 over L sine of n pi x over L, where n is restricted now to 1, 2, 3, 4, and so on, to positive integers. Okay, so that's your quantization right there.